Okay. Okay, so we are ready to look at our next module, which is module number 8, springs. And let's take a look at our learning plan first. So as we look at our learning plan here, you're going to notice that we're going to be looking at chapter 18, which starts on page 655 in your book and goes till 690. And we're going to be focusing on springs, okay, as a machine element and, incorporating them into designs. So I have the PowerPoint there. I'll be pulling that up in a little bit. I will be recording the session, so if you wanted to go back and watch this, and then you'll also notice that we're going to be doing some practice problems. They're going to be from the end of the chapter, not the examples in the book, and I'll explain why. And then we also have an in-class case study, something that's outside of the book, but it's going to give you an opportunity to do some calculations for springs and then go to a vendor website and specify a spring for an application. Okay. So you'll have practice problems to do here that are related right here for the examples we're going to be doing in class and working out. And then you're going to have an assignment that is going to mimic the stuff that we're doing here in class. So very much like what we've been doing up until this point. Now, additionally, I'm going to go back. As we look at this module, I will be posting the session recordings here. And then this is where your practice problems are going to be. And this is where your assignment number 8 is going to be. If we click on each, you're going to notice that the problems are listed. And then for the practice problems, as you know, there's always those extra little, 2 questions or so that I ask you to just put as part of your submission. And they're there again. So we'll make sure that you do those. And then assignment 8 is listed here as well. Okay. And by the time we get through, you'll have a good idea of what we're looking at there. If you wanted to, now is probably a good time to download the spring calculator if you would like. We can also do it later, but we'll be referencing that a little bit later in the lecture. Okay, so let me go back to our PowerPoint that is going to guide us through our chapter. So I'm going to click on our PowerPoint. It's a PDF. I'm going to zoom out just a little bit. And as it says here, chapter 18. So the objectives of this chapter are going to be really looking at springs in terms of an industrial application and where they're going to be used and different types of springs. We aren't going to get into the weeds of designing individual springs because springs are really a purchased part. So we're going to take it a little bit from the stance of being able to calculate if I have a physical spring in front of me, being able to calculate some important information about that spring. But then also our case study is going to deal with, here are some parameters, here are some design criteria, and now go out and find a vendor who makes that for you, okay? Because that's usually going to be what we're going to be doing when we're out in industry. So we're going to be looking at different types of springs. There are a ton of different types of springs, but we're going to focus on the most populars, which is going to be the helical compression springs. We're going to be talking about the stresses and the deflections for compression springs, as well as looking at those key characteristics that they're going to kind of cross over into almost every type of spring. If you took physics, and I know you guys all have, you would have done, probably a spring lab of some sort, Hooke's law, applying that, and you're going to see some of those things come back. So we're also going to be using a calculator that's going to help us specify a spring for an industrial case study or an industrial application. All right. Now, on the next page here on table 18.1, this gives us a category of different types of springs. And what's nice about this table is on the left-hand column here, it identifies the use or what's going to actually happen. What is the action that's going to occur? And then the type of spring that's going to speak to that. So for instance, if we're going to have an action where we need to push on something, then we're probably going to be looking at a compression spring of some sort, maybe a Belleville spring, maybe a torsion spring, depending if it's like that, and then and so on. So this table is kind of nice for helping you to narrow down going from the action to the type of spring that you're going to be involved in. Now, instead of looking just at a list here, if we look on the next page, this is figure 18.2 in your book, and this is going to be found on page 658. And this starts to look at the physical characteristics and like what they look like, each one of the springs. So the first batch of springs here you're going to notice that the arrows are kind of pushing in on these. These are all compression springs, okay? So we've got constant pitch, we've got a conical, a barrel, hourglass, a variable pitch, and these are all going to be that they're going to be in like their, what we call their free length, their longest length, and then you're going to compress down on them to operate, okay? I do have some here on my desk, so if you're in the classroom, you'll get the benefit of being able to kind of look at these, but I'm going to go underneath our camera here. Oops. Got to get it up and running. I thought I had it kind of closed out. This. So if we go underneath our camera, and I'll put this here, I do have a couple different types of springs here. Kind of in front underneath. So this is going to be just one of those regular compression springs. So you'll notice that I would press on it and then I can compress it. Okay, so that's a compression spring, kind of run of the mill. You'll notice that the wires that are going around here, the coils, are actually cylindrical in nature as far as the metal that's being used. You can also have springs, and this looks to me like a die spring. I don't know exactly what it came out of, but die springs very typically are going to have more of a rectangular cross section as opposed to a circular cross section on the diameter of the wire for the spring itself. So just a little bit different application. Obviously, a lot more stiff here. I can't even compress it, but a die would be what I would guess this probably came out of, something that's a very heavy compressive load. Another one here, this is a circular cross section on the wire, but very beefy. Again, I can't compress that with my hands, but it would be in an application where it would obviously be a very heavy force that would be compressing this, okay? The next one here is a barrel spring. This one's kind of really easy, but it's got a wider diameter in the middle and it's smaller on the ends. And as far as extension springs, the last one that I have here is really big. Okay, this one's pretty long. And we see springs in a lot of different areas. I mean, if you have a pen that has a retractable, you know, what is that? Would be the pen portion. I want to say lead, but that's a pencil. But even a pencil would have that. There's compression springs in there. Can you think of any other applications, even those who are virtual, any other applications where we see extension springs? Any ideas? Or that you can think of? Yeah, go ahead, Jacob. Suspension on your car, absolutely. When we look underneath, right, we can see the actual springs in there. Jesse. Those annoying door stopper things, they always kind of hit you on the way out, right? You get your ankle because it's like goes too fast. Yeah, mine's a little, yeah. Any others? What was that? Keyboards, yeah, underneath, right? There's little springs underneath there. Absolutely. If you look around our room, we end up seeing a couple springs in a couple places. The suspension on that, the front end of that motorcycle, right? We can see springs there. In the back, Jesse, do you see a spring in the engine? There's a valve spring. Yeah, absolutely. So, so compression springs are used in a lot of different areas, and they absolutely are one of the most popular. And we're going to see that the characteristics that we end up looking at are found in the other springs. They're just calculated a little bit differently. Okay. Then as we look back at our PowerPoint presentation, you're going to notice underneath here, there's some also extension springs. Now I have a couple of extension springs here as well, and I'll have these up in the room so you guys can, you know, come and play with them if you want to. But extension springs, I go back underneath here, these are going to be ones that actually are in what we call their solid length normally, but then they're pulled apart, right? And so they're going to do their work being pulled apart. Some of them are going to be more stiff like we see here, or not as stiff, okay? This would have probably been the type of spring that if you did that Hooke's Law experiment that's very popular in physics classes where you put different weights on the spring and you see how far it extends, extension springs would have probably been used for that. So extension springs, any ideas about where those are used? Oh, virtually, I've got a chat. Mattresses, that would have been for the compression spring, right? Yeah, that's kind of like these guys, right? Don't they look like that? Kind of that barrel look. Extension springs. Where do we see extension springs? I think, Jesse, that would have been your application, right? On the door. Yeah, that pulls the door set like a screen door or something. Where else? Anytime you need a latch, right, that needs to stay closed, if you pull it and then it goes back down, right? A spring could be used for that. Possibly an extension spring. Yes. Oh, lawnmower decks. Yes. Yes. Those like little levery thingies, right? Yes. Yes. Absolutely. Good. Others. A trampoline. Yes, they do. They do. We had a trampoline a long time in our yard. That was fun. It's fun. Okay, good, good, good. Then the next types that we have here, there's the drawstring or the drawbar spring. This is kind of like an extension spring, except it actually has a compression spring on the inside here that it's utilizing. And then I don't have an example of that one here, but I do have some torsion springs. Tell me, where do we use torsion springs? Back underneath here. So this one's a torsion spring, okay, where you would kind of, you know, go one way or the other, but this is its orientation. Another one. What does? A mousetrap does, and there's actually one in the back of our room. I think inside of that door there. Eric, you want to take a peek? I think there's one in there. They do use a torsion spring. What other common household item uses a torsion spring? There, a clothespin. I happen to have one here. Yes, it's a clothespin. Absolutely. So that's one. Garage door. Yes. Yes, yes, yes. Any others? Oh, like a leaf spring type of, or no? Oh, a torsion bar.
They're basically bars that have two like wings on them.
Okay.
So when the suspension moves, it twists the bar between the two.
Oh, interesting. Okay. Oops. On a miter saw. Oh, does it, Jonathan? Trying to think, on a miter saw. Oh, when you pull it back and like up and down, right? Yeah. Good. And what's kind of fun about probably as we're talking about these different things, kind of keep your eyes open, you know, around you to see where have you been noticing like machine elements that like in your everyday life in some cases, and springs are everywhere. So it's a really important subject, and it's something that you're going to probably find a lot of applications for when you're out in industry. Any other thoughts or ideas about the springs that we've talked about? Okay. The next type of spring that we have are going to be Belleville disc washers and springs. And we have a resident expert who's used these before. So Ryan Weister, who is is one of the instructors in our program. If you want to come up, you can. I have a couple here actually. So Ryan used these out in industry, right?
Yeah.
Use various designs.
Yep. So I'll go underneath. So if you want to explain the.
Yeah, sounds good. So yeah, Belleville disc springs, or sometimes they're just called disc washers. They're used in a variety of applications, but the cool thing about these is you can get a pretty high force in a pretty small, compact area, right? Like if you had Belleville washers stacked this high, it would probably be like thousands of pounds. The cool thing about it is you can actually stack them in various configurations. So this first one here, this is spring force in the Y direction and spring deflection in the X direction. So this is an example of one washer. So your baseline would be one, right? You have your starting point for force and deflection. If you stack them in parallel, you are doubling your force, but your deflection's the same. So you can stack a bunch of these in parallel and just increase your force, but it only travels the same amount. So you compress it a 1/4 inch, you could get, 10 pounds with two of them instead of 5 pounds with one spring. And then you can also stack them in series like this. So your force is going to be the same, but you're going to get more travel on it. So you could stack 5 of them up like that in series, and your force would still only be, let's say, 5 pounds, but now you can get an inch instead of a 1/4 inch of travel.
See, underneath the camera here, I'm just gonna show underneath the camera. We have a couple of these. This is what they are, right?
Yeah.
Mm-hmm.
Yeah. So you can stack them in a parallel like this, or you could stack them on top of each
Back to
other
back.
in series.
Mm-hmm. I know, it's hard to,
Yeah, hard to see that, but
yeah, so just kind of like this orientation. I know it's not-
yep.
it's
So that would
weird.
be a set in parallel and in series, like we're going to show in that other picture there.
Then
Which
you
one
can
do you
just
have?
go back. Yep.
So then you can also stack them in combination, so parallel and series, and you're getting more deflection and more force with it. So a unique type of spring, a little different than compression springs, but they're used in a variety of applications. I'll show you a few in a minute. Any questions on stacking them or how that works?
And they're literally, they look like washers that are cupped.
You'd have to like put them in the tube or.
Yep. Yep, you either put them in a tube, like you say, or a shaft. A lot of times you'll have a shaft going through and then it'll be inside a bore housing as well. And there'll be something, some sort of motion in between that you're supporting. They're used a lot with hydraulics and pneumatics as well. So you use the hydraulics or pneumatics to release whatever you're clamping, and then you use the springs to clamp the system or load the system. So this is one application we can take a look at. So this is a machine tool spindle with a stack of disc springs inside of it. I'll just show you a machine here quick. So this is the company I actually worked at for a while. So these are big milling machines that we made, and this is a machining spindle. So I imagine most of you are familiar with that, but this is like a 50 taper Cat 50 machining spindle. So at the end of it, a tool rotates, right? So you can cut material and remove material from steel. You guys all took manufacturing processes, so you have an idea. So inside of here, you need some way to clamp that tool to prevent it from flying out while you're machining. So what's very common in machine tools is using these disc springs inside of that in a mechanism called a power drawbar. So the springs grab the end of the tool. There's a little knob on the end of the tool holder. It grabs it with a little chuck, and then the springs clamp it shut. And then when you want to release the tool, you turn on the hydraulics and it releases the springs and allows you to pull the tool up. So it's got a mechanical system by the springs that keep it shut. So in case you like hit the E-stop or you lose power, that tool doesn't come flying out. So it's spring loaded clamped. So that's where I was saying with hydraulics and pneumatics are used a lot with these. So you spring load it, it's mechanical, it's safe, it's not going anywhere. And then you use the hydraulics to release it. So if you looked inside of that spindle, you took a cross section through it. Here's the end that grabs onto the tool. The tool would be on the end of here. And then this mechanism is inside here, and there's a bunch of the springs stacked up. And you have a hydraulic piston to release it. Any questions on that? Yeah, it kind of depends on the design, but they stack a bunch in parallel and in series to get a pretty a high force for that. And like you were saying, Eric, it's inside of a bore to hold it, and then there's also a shaft going through it. In this case. So one other example I'll show you quick. So miter saws also have Belleville washers on them. So the actual table, so on a miter saw, you can rotate the table back and forth. right? To do your different angled cuts. Probably have an image one rotated somewhere here. Maybe not. But you can rotate that table back and forth. So there's a bolt in there and a nut, and then there's actually, they use one Belleville washer to spring load that system to keep it clamped. So you can, when you rotate it, it's preloaded, so there's not any play inside of it. So that's another application of a washer. And that's just a single washer used, and it's just bolted together in the system, preloads that nut and bolt, and it stays in there.
Any questions? Yeah, it's not a typical type of a washer. I had known that they were out there and I kind of understand their use, but I had never worked with them and Ryan had. So I thought it would be a great opportunity for him to share with us, you know, where and how they're being used. Thank you.
Sounds good, no problem.
Thank you.
How do they like wear and fatigue?
What's that?
How do they wear and fatigue over?
So the question is, how do they wear and fatigue? Come back here, Ryan.
Yeah, I mean, it's just like, like any other piece of metal, it's going to have a finite life. But you would just use the vendor to look up the life for that specific spring and the equations for that. But they do design them, like most springs can have a pretty high cycle count. So as long as you're within the working range of it, that's specified by the manufacturer, I mean, you're in like millions and millions of cycles. So you just want to make sure you design within the specified range and load of the spring you select with any type of spring.
And I imagine these can be made out of all different types of materials, just like springs can.
Yeah,
Yeah.
yeah, most commonly a high strength steel.
High strength steel. Okay. All right. Cool. Any other questions? All right. All right, cool. Thank you. Thank you. Okay, so we're going to shift gears and we're going to look at helical compression springs. And helical compression springs are going to be, as we know, probably the ones that we see the most. We probably see these more often than any others in our everyday life, but also in industry, they end up being very popular as well. So what we're going to do is we're going to kind of go over some vocabulary, but then also some concepts and characteristics that are going to be used in designing them and kind of calculating, you know, different things about them. So first of all, the spring that we see here, this is using round wire that is wrapped in a cylindrical form at a constant pitch. So the pitch is going to be the distance from one point on one of the coils to the very same point on the next coil. So very similar to when we look at like pitch on a thread or something like that. This is going to be that same definition, but it's going to be from coil to coil linearly along the length. Okay. Now, and that's going to be even. Well, you can have variable pitches, but most often it's going to be an even value all the way down. The inner diameter here, when we look down the middle of our spring, the inside diameter, the inner diameter is going to be the smallest diameter. It's the diameter that would, for instance, fit over the top of a rod or a shaft in order to keep it like in an orientation. Then we have the outside diameter. So that's going to be the very outside diameter as we see here. And then we have a mean diameter. The mean diameter is going to be exactly halfway in between that inside and that outside diameter, or we could say it's half the distance of the diameter of the wire. So the wire diameter is going to be this thickness as we go around each one of those coils, okay? And we're going to assume all the applications that we're looking at are going to be circular or round wire that we're going to be dealing with, okay? Now there's also different end conditions that springs can have, compression springs can have. If we look at figure 18.2 at the bottom of page 658, right down here, we are going to see a couple of different. Now, the first one here, it says plain ends, and all that is literally cutting off the spring after it's been made. And you're going to notice that there's a portion of the spring kind of right there, okay? This isn't done very often because when you have a configuration like this, you can imagine that this spring isn't going to sit flat. All right. It's going to be like tipped at an angle, but it is considered a plain end. Most often you're going to either see squared or closed ends. Okay. Or actually ground off so that they're nice and flat. And we have some examples of exactly that here with the springs that we have. I don't know if it's easy to put it underneath here, but this would be a ground flat one. So you can see that it's going to be nice and even. So when it sets down, it's going to sit nice and flat, okay, on both ends. Here's another one that is ground flat on that end. And so when we set it down, it's not like rocking at all. So, so end conditions are going to be something that you want to be aware of depending on the application. If it needs to sit down into a bore, you want it to sit nice and flat so that the travel and how the force is going to be in there is going to be linearly or down its axis. If it's tipped on an end because it doesn't have the ends that are going to be ground so that they're flat and sits nice, then you could have the possibility of kind of being cocked with your force. Okay. So and then this is just a left hand and a right hand. Okay. Now the other thing here, because this is going to come up as well, is you'll notice that we have a series of coils. Okay. So the number of coils that go around at that distance, which would be the pitch, is going to then set up how long or short the length of each one of these springs is. Okay. Now there are standard wire diameters on page, starting on page 660, there's a table 18.2. These are standard wire gauges and diameters for springs. The wire diameter is important. So the material that we make it out of, as well as the diameter itself, as those wire diameters get smaller, you're going to notice that the gauge number gets larger. It kind of moves in the opposite direction. So the standard sizes that we would see are going to be on page 660 here. And so this table gives us the wire gauge sizes, the diameters for each one of the springs. Now the gauge is going to be on the left-hand side here, okay, usually in the form of a number, and then it corresponds to a diameter, okay? And then this is steel wire gauge, and then we have music wire gauge, and that's going to be on a different scale as well. You're going to notice that the music wire, starts a lot smaller than what the steel does, okay? And it just depends on the different applications. Then lengths. Lengths are going to be very important too, especially when we're trying to incorporate them into a design. So the different lengths that we can get out of a spring are, number one, the free length. The free length is going to be the length of the spring that it assumes when there's no force on it. So as I have a spring, for instance, sitting on my table here, okay, I'm just going to kind of put it on my underneath. Without any force on it, this overall length is what we call our free length. Okay, so just sitting, no force on it at all. Okay. Same thing with this one. This would be the free length from the very top to the bottom without any sort of force on it. Okay. The solid length is going to be when the spring is collapsed to the point that all the coils are touching. Okay, so solid length is then going to be, if I would take this one, probably my best chance at going all the way. If I go all the way and they're all touching at once, that's going to be the solid length. Okay, and what that distance would be. So collapsing it all the way. Here, I know I'm not going to get it to a solid length, but each one of those would be hitting each other. Each one of those coils. The operating length. The operating length is going to be a length that's going to be the shortest length during normal operation. So what we're anticipating is that there's going to be some sort of an operating, in and out, okay? And there's always going to be constant like tension, if you would, on that spring. So this is going to be the operating length is going to be the shortest that it's going to get while it's actually, doing what it's supposed to do. So if I go underneath here, so we're not at the solid length, but it's going to be like somewhere in between here-ish, the expected shortest distance. That would be our operating length. And then lastly, an installed length. When we put a spring into a mechanism, we are going to have a little bit of tension on that. So that's going to be the shortest length to keep it actually installed with a small amount of compression on it. Okay. So when it's in its working state, it's going to be between this installed length and its operating length. Okay. And then really, it's never intended to get down to the solid length. That's just like what it is when all of them are collapsed. Now, there's going to be forces associated with each one of these lengths. So there's a force at the solid length, a force at the operating length, a force at the installed length, and then a force when we have our free length. So starting with the force at the free length, you can imagine when it's just sitting and there's no, and the length of the spring is free to just be what it is. Oopsie. The free length force is 0. Okay. It's just what it's doing when it's sitting here right now. Okay. So free length is always 0. The installation is going to be when I compress it that little bit to be inside of whatever I'm installing it in. Okay. And there's going to be a force associated with that. So I'm pressing on that. There's a little bit of force when I want to do that installation. The operating force is going to be more. Okay. And that's going to be, closer to wherever it's going to be. It's short its length when it's operating. And there's a force associated with that. And then there's also going to be a force when I want to collapse this the entire way when it's solid. Okay. So all of those kind of correspondingly go along with. So you can imagine, like I said, the free force is going to always be 0 because it's when the spring is just sitting there. The initial force is going to be a small amount. Operating force is going to be a little bit more. And then the highest force is going to be when we collapse it all the way to be solid. Okay. Now, to calculate that, we need to know something called the spring rate. So again, kind of going back to your physics class, I'm certain when you did that Hooke's Law lab and you worked with the springs, you probably calculated a spring rate, and it was using the letter K. It's like the standard letter for it. And spring rate is going to be that relationship between the force that's exerted by the spring and how much it deflects that spring. Okay, how much it deflects that spring. So if I go back underneath here, if I look at how much force is it going to take me to get to whatever this measured length would be, that's a function of this spring in terms of its spring rate. Okay, then what it allows me to do, once I know what that spring rate is, now if I collapse it a little bit more and I want to know what is the force at this new distance or this new length, I can predict that based on this spring rate being the same throughout the entire operation of that spring. Okay, so it helps to predict values throughout the different lengths. Okay, if I go to page 662, the equation for spring length in a number of different forms is there for us. Okay, so down on the first column towards the bottom here, these are our options for spring rate. Now, in its variable form, kind of generic form, we look at spring rate as being the change in force divided by the change in length on that spring. Okay, so it's a deviation of. So whatever I start with to whatever I end with, in each case, the force and the length. Now, this is the force is in the numerator, and the length is in the denominator. So that means that spring rate has units of force over length. Okay, so spring rate is going to be, for instance, in terms of English units, it's going to be pounds per inch. Okay, in terms of metric units, it would be newtons per millimeter or centimeter, but most often millimeter. Okay. So you'll notice here then what they do is they kind of take this and they expand it out when we're looking at different scenarios. So if I want to know what the, any one of these variables are, knowing the spring rate, I can take my operating force minus my installation force. Okay, so my installation force is going to be a little bit less than my operating force. And what I can do is I can divide it by the length initial, which is going to be longer, minus the length when it's collapsed underneath that operating force. So notice that the O's go with the operating and the I's go with the initial. Okay, so they line up with their force. Let's say I have operating force in regard to free length. Okay, in this case, you have FO or operating force by itself on the top because we would subtract off the free length force, which is 0. Okay, that's why it's not there. So free length force will always be 0. So even if I still use the free length in the bottom, it would be a minus 0 on the top here because the force at free length is nothing. Okay. So then we have our free length, knowing our free length, and then minus whatever that operating length is going to be, again, through that spring constant. Okay, so we're gonna find that we're gonna do some example problems, and you're gonna have homework assignment problems that are going to, you know, try to solve for one of these variables. So if I know the spring constant, what is the operating force? You know, when the free length is this, that kind of thing. Okay, so we'll be manipulating this to kind of make it work or help us solve for some unknown variables. So questions on spring rate. I'm sure you've kind of come across that before. Spring index. Spring index is going to be the ratio of the mean diameter of that spring to the wire diameter. Okay, so thinking back or looking back at that illustration on the top of page 660. Okay, here. This illustration right here. So our mean diameter is going to be right in the middle of, right between the inside diameter, the smallest diameter, and my outside diameter. And essentially it's going to be the outside diameter minus that wire diameter. That's going to be my mean diameter. And what I'm going to do is I'm going to look at that ratio, that mean diameter divided by the diameter of the wire. And design recommendations say we want that C, that spring index, to be greater than 5. Okay, greater than 5. If it's less than 5, it's going to be hard to form it because it's going to be taking a sharper curve, if you would, around, and it could actually form cracks when that's happening. And then that's a failure. It's not going to perform the way it's supposed to. So this ratio we want to be greater than 5. Okay, the larger the C, the lower the stress then internal stresses are as we're making that that spring. The next is going to be number of coils that we're always interested in spring. So number of coils is called out as capital N, and there's something called active coils. Active coils is going to be how many are actually actively doing the work when this is in operation. Now, if we have squared and ground ends, we end up losing 2 of the total coils as active coils during operation. Okay, if we have plain ends, they're all available, but plain ends aren't used all that often. Okay, but all of those coils are active for us. And then if we just have plain and ground ends where we're not squaring off the ends, then we lose just 1 coil. So you have to know, you know, what situation you're in. And you can always look back to figure 18.3 on page 658, where we had seen those different configurations, or examples of these are here in class as well to kind of, you know, make sure you see them. But if this is going to be something you're going to be interested in, it'll be told to you in an example problem what the end conditions are, so that you can then calculate or determine how many coils you'd be using in an equation. The next characteristic here is going to be pitch. Pitch refers to that axial distance from one point on a coil to the corresponding same point on the next coil. Okay, so it's really, like I said earlier, it's going to be like the pitch that we see on a thread. So it's the relationship between in the free length to the end conditions of the pitch. So if I look underneath, okay, here, I'm going to first kind of try to illustrate pitch. So if I have my my spring here, and what I want to do now, it's not very easy to do on a circular feature like this, but what we would want to find is maybe a point along that diameter of the wire, and we would measure then from one coil to the very same point on the next coil. And that distance, that linear distance along the length, would be the pitch. Like I said, it's very similar to when we determine the pitch on a thread. Okay, one point to the next, it's that distance. Okay, now to calculate the pitch or to see the relationship, there are a couple of equations that they're identifying here. So right in the middle, right after that pitch section there, you're going to notice that we can relate the free length, L sub F, is equal to small lowercase p is going to be our pitch, times the number of active coils. So we have to know, are we squared and ground? Are we only squared? Are we plane and ground, or are we just plane? Okay, because the equation changes a little bit depending on the number of coils that are active. And then once we identify that, then we're going to add either 2 times the wire diameter, or 3 times the wire diameter, or just 1 time the wire diameter, or not at all, okay, depending. And then this is going to be how we can find our free length, knowing those, or we can rearrange to solve for our pitch, okay? And you'll get that opportunity in the problems that we do. All right, so we'll be back to this to kind of, help make sense of it. The next thing that we have here is pitch angle, okay? So pitch angle is going to be looking at the angle or the slope, if you would, of the coils as they wrap around, okay? And to find that pitch angle, which is lambda, is going to be equal to the inverse tan function times the linear pitch from above divided by pi times the mean diameter of our spring, okay? Again, you'll have the opportunity, you'll get to solve this a little bit later as we look at some examples. Now, additional installation considerations. What happens when we compress these springs? The diameters get larger because of the compression that's happening. So if we're going to be putting them inside of a bore or over the top of a rod or a shaft, we have to be sure that we're accounting for that in our design, okay? Now, very typically, just kind of a run-of-the-mill number is to make your hole 1/10 larger than what the wire diameter is on your spring. So if I look underneath my camera here, and I use my spring that I have here as an example, if I measure the diameter of my wire here, the hole that this would fit into, so the diameter of the bore that this would fit into, okay, has to be 1/10 larger than this diameter of that wire, okay? Or we can calculate it more accurately, and it comes out to about the same using the equation that we see here on page 660 in that installation considerations section. So here you're going to see 18.3. Again, there'll be an opportunity for you to use this equation, but it's really kind of comes out about 1/10 larger, okay? But more accurately, it would be this, a way to calculate it, okay? And then the ID would be exactly the same, about 1/10 or 0.1 times that wire diameter. We would make it larger. Materials used in springs. So we already talked about the sizes of the wire, but now the different types of material. Now, for the most part, any elastic material can be used, okay? So, I mean, you see plastic springs, you see, all different nylon springs. There's all different types of material, but most often in industrial applications, we're going to be using metallic or metal wire, okay? On table 8.3, page 663, it's at the bottom of the page there. It actually starts the list of common materials that are used for springs, okay? So most common really being a high carbon steel, something that, is nice and tough, that can spring back. As you know, it has the ability to deform, but then, kind of go back to its original shape. So ASTM number A227. Now they have a column here for relative cost. So they're starting there. Metallic steel springs are going to be your most cost-effective option out of the gate, okay? And you're going to notice they have some temperatures that they run within. And then as you move away from there, these are all compared back to that steel. So when possible, you want to try to use something that's most cost-effective as long as the environment works for it. So if it's a die spring, for instance, you're probably going to have lubrications in there. So steel types of springs are going to work well, okay? But if you're in the food grade industry, steel that is uncoated, probably not so great. Now we've got to look at maybe some other alternatives like stainless steel or other coated types of springs because they can't, you can't have something corroding around food. Okay. Other industries as well, depending on the environment that you're in. If there's a lot of humidity, steel might not be a great choice. You might have to go with something else, or at least coat them so that they don't rust. Okay. So a lot of different options. The next one here is going to be the music wire. Okay. Now the music wire is more expensive, but again, not terrible. There's some oil tempered, and as we turn the page, you're going to notice that there's some other types here. And then that cost, is going to be, again, compared back to the one, which is the steel. Okay. So, so lots of different options for materials for spring, obviously. Now, loading and allowable stresses. So once we start putting loads on this and we start, cycling them, there are going to be stresses that these springs are going to experience. And so we want to be aware of those and know how to calculate them and then see if they're okay, if they're applicable. So there are different service classifications: light, average, and severe. And if we look on page 663, there is a description of each type of application. So you would want to determine where your application would actually fit in. Okay, so a light service is going to be where maybe you don't even have loads that are oscillating. It's just going to be right there, and it's going to create like a preload. But it would be up to 10,000 cycles of loading and a low rate of loading. So kind of non-impact, not anything that's too severe. Light service. Medium or average is going to be a typical machine design situation, moderate rate of loading, and up to 1 million cycles. And then your severe is going to be rapid cycling, over 1 million cycles, possible shock, impact loading. So something like valve springs in an engine are a good example. Okay. So once you kind of determine where you're at on that service, then what you can do is you can look at determining what then your design service is going to, or your design stress is going to be. So if we go back underneath here, starting on the following page, 664, we have there's 6 different materials. So the first one is here at the bottom of 664. Then on 665, there's going to be 3 more. And as we turn the page, there's going to be a couple more. Now, each one of these charts is a different grade of material. So you'll notice that on the top of page 665, figure 18.9, we have ASTM A228 steel wire. And you'll notice that the horizontal axis is going to be the wire diameter in inches. So we find what the wire diameter is that we have. And then what we're going to do is we're going to take that wire diameter wherever it's at, and we're going to go up to the service line that applies to the application we're dealing with. So light is going to be the highest, average is going to be the middle, and then you're going to notice that severe is going to be on the bottom. Okay, so I'm going to just pick 0.13 here. I'm going to go up to the middle line, and then I'm going to go over and I'm going to read the axis for what my design stress would be for that material. Okay, so this is going to be then when I calculate my stress, I'm going to compare it back to this chart. This is what we call the allowable or the design stress. Okay, what's going to be something that's okay for that to take. Now, to calculate, or what we're going to be calculating is we're going to find that the stress in the wire is going to be a torsional shear stress. Okay, you guys looked at torsional shear stress back when you were in strength of materials. Torsional shear stress is going to be torque times the distance to the outermost material divided by J, which is the polar moment of inertia. Okay, so this tweaks that equation slightly. Okay, and it adds a little bit to it. So if we look at equation 18.4 on page 666. Okay, I'm going to go down to the bottom here. The bottom of the page here, this is the section on stresses and deflection. It talks about that standard torsional shear stress equation, which you would have used back in strength of materials. And it's going to take that and it's going to add some spring stuff, okay? Some spring stuff. So torsional shear stress is going to be tau to us. We're going to look first at the equation right here, and it says 8. That's just going to be a factor. So 8 is just a number that's going to be a multiplier on top there. Capital K. Capital K is going to be what we call the wall factor. The wall factor is a factor that is going to be calculated, and the equation for the wall factor is on the following page in the first column, 667. And we're going to take 4 times our spring index minus 1, and then divide by 4 times our spring index minus 4, and then multiply or plus 0.615 divided by that C. This looks at the curvature of the actual spring itself, okay? And this wall factor, this K, is going to be placed in the top of our equation. Now, because it's using C, if you recall, C is recommended to be greater than 5. Okay, so this was where if it's too small, if C is too small, it's going to be going around a diameter that could cause that wire to crack. Okay, and so what this wall factor looks at is exactly that, using that curvature, that C value, making sure that it's higher than 5, and then plugging it in. So our C factor is very much part of the amount of stress that's going to be created, because K is in the top here of this equation. That's where, you know, basically we're using C for that. So the higher the K value, the higher the torsional shear stress. The F, capital F, is going to be the force that we're going to be applying during that stage, if you would. So if we're looking at the stress at the operating length, this is going to be the force at the operating length. If we're looking at the stress at the solid length, then this is going to be when it's compressed all the way down. What's the force at the solid length? DM is going to be that mean diameter. Okay, so that's going to be the difference between the inside and the outside diameter of our spring as we look down the center of it. So again, back to page 660 at the top here, that mean diameter is right in the middle of the ID and the OD. Okay, to find it, you simply take that outside diameter and you just subtract the wire diameter, and you've got the mean diameter then. Okay. Then underneath, okay, the things that help bring the stress down, oopsie, well, pi is going to help us, but then notice that the wire diameter, the larger or the thicker that wire diameter by a cubed root is going to help us with bringing that stress down. So the thicker that wire is in our spring, the lower the stress is going to be torsional shear stress wise. Okay, which makes sense, or material. Now, the only thing that they changed here was they kind of swapped out for using C in that equation. So it's really the same values, but different variables to get there. Let's look. So we talked about the wall factor. K increases the amount of shear stress, and then the spring index recommended to be a minimum of 5, looking at that equation. Now, deflection. Deflection is something they refer to when there's a change of length due to the application of a force. Now, when we're looking at compression springs, it's always going to be in that direction along the length. So we're always going to go from our free length, and our deflection is going to be in the direction of making it a smaller length overall when that force is applied. If we're looking at extension springs, that deflection is then going to be, okay, the solid length starts here, but then my deflection is going to be, what is the difference when I pull it? It actually gets a larger distance in that case because of the nature of the direction of the force, okay? So linear deflection is going to be a small letter F. Angular deflection, so in the terms of like a torsional spring, is going to be in terms of theta. Okay. Now the equation for linear deflection, that is going to be found on page 667 at the bottom of the first column. So angular deflection is right here. And then linear deflection is going to be down here. Now, a couple new variables. We'll zoom in here. 8 is just a factor again. F is going to be the corresponding force to whatever your, operating length is. If it's at the, like I said, operating length, it's going to be the FO. If it's at the installation length, it's going to be FI. If it's going to be at the solid length, it's going to be FS. Here's our, the cube of our mean diameter. NA is the active number of coils. So we need to know, do we have ground and squared ends, or is this just plain ends, or is it just ground? Okay, and then go back and determine how many actual active coils there are. Now underneath here is G. G is called the shear modulus of the steel that we're using in our spring. Shear modulus, tell me what shear modulus is. Do you guys remember from strength of materials? There was modulus of elasticity, and then there was shear modulus. Modulus of elasticity was when we pulled on a specimen in tension, and we wanted to know what was the slope of the line in that elastic limit, right? That was the modulus of elasticity, capital E, and that was based on a tensile test. Shear modulus is looking at how does our material twist. Okay, so it's looking at a rotational sense instead of, or a torquing sense instead of as a pulling. So shear modulus, because of the nature of a spring, it kind of, as we push it down, it torques as well. And that's where the shearing is happening. So we need to apply and look at what is the shear modulus of the material that our spring is made out of. So that's underneath here. So the higher that shear modulus is of the material, what happens to the deflection? It's going to go down, right? Which makes sense. It's going to be a stiffer material. It's going to be a stiffer material. Okay. And then you're going to notice that our wire diameter, the larger that wire diameter, the deflection goes down as well. So I see that directly underneath my camera here. If I try to deflect this spring, okay, this diameter, or if I try to deflect this spring, this one's going nowhere under my own force, okay? That wire diameter is way thicker, okay? Much stiffer spring than this one, okay? So that wire diameter plays into that, which I think that's pretty standard and makes sense. 18.4. Looks at the wall factor versus our wire, round wire. So we have a spring index here, which is C. We find where our spring index is, and you'll notice that 5 and above, we've got a nice solid line. And yes, there's some curvature here, but it really starts to go up after 5. And that's kind of the point. Like, you don't want to be over on this side. So you want to be 5 and to the right. And once we go up and over, that's going to help us determine our wall factor on the chart, as opposed to if we didn't want to calculate it. But we can calculate it as well using the equation we see here. But you can physically see like what that looks like and its behavior. So here, the wire, here's the shear modulus and the modulus of elasticity, so tension and that shear. So G is going to be that shear modulus. So depending if you're in English units or in metric units, you can be in PSI or in pascals or gigapascals. And then on the right-hand side here, this is going to be the comparison of the modulus of elasticity, but this is in tension when we do a pull test on it, okay? So the one that's applicable for our springs is going to be our shear modulus, not our tensile modulus, okay? Okay, so let's do a problem. You've been listening to all these terms and looking at equations and looking at charts, but how are we going to, how are we going to put this to practice? So what I want to do is a couple problems here that are going to mimic some of the homework that you're going to have assigned and kind of get us, used to using some of these variables. So the first problem we're going to do is actually on page 689. So we're going to skip to the end of the chapter. And we're going to look as an example problem, and this is going to be one of your practice problems that's assigned. We are going to be looking at problem number 1. And the problem statement says we have a spring that has an overall length of 2.75 inches when it's not loaded, and the length of 1.85 when carrying a load of 12 pounds. What they want us to do is they want us to find the spring rate. Okay, find the spring rate. So if I go underneath and we look at page 689, the very first problem here, this is the statement that I had just like transcribed into our PowerPoint. Okay, so what we need to do is we need to find our K value. We need to find that spring rate. So if we go back to our PowerPoint presentation, you're going to notice that it asks a couple of questions here, like, what are the variables that are given? What is the equation that you plan on using? And what are the final units that you think we're going to be looking for? So what I want you to do is I want you to, and I'll give you a hint, you're going to find the answers here or kind of get started on page, let's see, 662. Okay, 662 is where spring rate is. So go ahead, and what I want you to do is on a piece of paper, just start by writing down the variables that are given. As you read this statement and you look at the variables on page 662 in regard to spring rate, try to line those up with the description. Then what is the equation you're going to use to calculate the spring rate? And then what are the final units you're expecting for this problem? So I'm going to give you 5 minutes to kind of investigate and start this process. Okay, so let's start looking at answering these questions down below. So to kind of see how we're going to approach this. So I'm going to actually start with the second question. What equation will you use to solve this for spring rate? Sure. Well, I'm going to start with the kind of variable form first. So K is going to be equal to the change in the force, right? Divided by the change in the length. So Brandon already went to the next step. So before we identify our FOs and our FIs and our LFs, let's go back over here. What is given? So if we know that the equation we're going to use is going to be the change in force over the change in length, now we've got to look up in our problem and figure out, okay, what are the lengths? So Brandon, what did you have for our givens? So LF, which is the free length, is the 2.75 inches because it says it's not loaded, right? So that's going to be our free length when it's just sitting on the table by itself. So capital F, L sub F, 2.75 inches. Okay, what else do we have given here? We do know our operating length. So it says here we have a length of 1.85 when carrying a load of 12 inches now, or 12 pounds. This probably could be operating length. We're going to assume that because it's probably going to be the operating force that it's going to see, but it could also be an installation, and they're kind of very similar, right? One is just to put a little bit of load on, and then the other one is going to be like the regular load. So it doesn't necessarily, it doesn't necessarily need to be one or the other. They're very similar in nature. So we're going to say LO is equal to the 1.85 inches, right? And then our corresponding force at that operating length, compressing it, is going to be FO, and that's going to be 12 pounds. Okay, so I'm going to go back underneath my camera here. And what I have so far is this. Okay, the beginning of our problem. So we know that our spring rate, okay, spring rate, and this is equation, oh, I put it up there, equation 18.1. And this is on page 662. This is the spring rate. That's going to be K. It's a lowercase k, lowercase k. Uppercase K is the wall factor. Lowercase k is going to be spring rate. Now, what we're going to do is we're going to take this and we're going to fill those values in. Okay. So we're going to say K is equal to, and I'm going to, now remember, don't do a slash. Always do up, down, numerator, denominator. And also I require when you guys write these out, you have to show your units in all phases of the problem. I want to see your work. Okay. I didn't get the pleasure of having you for other classes. So I want to see, I want to see your work. Okay. So these you have to write out and you're going to show me the units in all phases of the problem. So now what we're going to do is on the top here, this is where our forces are going to go. Now we're only given the operating force, right? But we have an operating length and a free length. So normally there's going to be a force associated with each one of our lengths. And if we would say the force at the free length, what would that number be? 0, exactly. So we're going to see that up on the top here, we're going to be the operating length minus, I'm sorry, the operating force minus the force at the free length, but there's no equation in there like that because this goes to 0. All right. But now we can still use our free length in the bottom. So then we're going to use our free length minus our operating length. Now, why did I put them in the order I did? Notice on the top, I did the operating force first, and then the free force, which is 0. And then on the bottom, I did the free length minus the operating length. Go ahead. So I don't have any negatives. That's what it is. Okay. So your K factor is always going to be a positive value. All right. And it's going to then give us units of, okay. We're going to put that in just a second. So I'm going to put my FO on the top, 12, and I'm going to write out pounds, divided by my LF, which is 2.75 inches, minus my operating length, which is shorter, 1.85 inches. Okay. So now as I look here, what are my units going to be for spring rate? Pounds per inch, exactly, because we're trying to say, okay, how many pounds does it take me to go a unit of one length? That's what I want to know. And that's then what I can apply anywhere. I'm able to then predict whether it's a length or a force or calculate a spring rate. Okay. So now I'm going to take 12 and I'm going to divide it by 2.75 minus 1.85. Notice I have my units in all phases of the problem. Do not leave the units off here. I want to see them. Okay. You have to write those out. And if you roll your eyes, that's okay. I'm not offended. I don't want them to magically appear. They are not what? They are not Lucky Charms. Okay. They're units. They're units. We need to reconcile them. And that's going to always be your clue at the end of a problem. If you end up with the correct units, you will know that you set it up correctly. Okay. It's a big deal. Big deal. Hopefully you do that in a lot of things. Okay. So if I take 12 and I divide it by my denominator here, what do I get for my number for K? Yes, 13 1/3, right? Repeating, yes. So 13.333 all the way, and it's going to be pounds per inch. Okay, pounds per inch. On the final, if you put it in pounds/inch, I'm okay with that. But when we're working it in a problem, it needs to be numerator above the denominator, up, down, not in a slash, because you need to see, not just I want to, you need to see where things appropriately cancel. It's a big deal to me. Okay. Even if you say to me, well, that's the way I always do it. That's okay. In my class, you can do it like this. Kind of like when you have a boss and they're like, I want you to do it like this because that's the way I want you to do it. Or at a company when they have certain ways, right? So in this class, I do want to see that. Okay. Okay. So that's going to be what we have to look for. So there is the spring rate for problem number 1. Okay. For problem number 1. Let's now look at our next example problem. You're going to notice that if we go back to our slides here, make sure I turned I think I did. We're going to go to the next problem. So let's do problem number 3. Okay. This one, a spring has a spring rate of 76.7 pounds per inch. Okay. At a load of 32.2 pounds, it has a length of 0.83 inches. Its solid length is 0.626 inches. They want us to compute the force required to compress the spring to its solid length, and they want us to compute the free length of the spring. So 2 parts to this one. We'll do the first part first. So here again, what variables do you know? What equation will you use? And what are the final units for each? So what I'm going to do is I'm going to pause the video right now, and I'm going to give you 5 minutes to kind of do that same process again, and then we'll compare in just a little bit and talk it through.